In Part 9 of the Unit 6 notes, we are going to be covering metallic bonding. Although metals are not ionic, they share some properties with ionic compounds. The bonding in both metals and ionic compounds is based on the attraction of particles with different charges. Metals often form lattices in the solid state, which are similar to ionic crystal lattices. While the structure might initially appear to be similar, the behavior of the electrons is very different. Metals bond together with a sea of shared electrons. This sharing is very different from a covalent bond, in which only two atoms are involved. The electrons in metallic bonding are mobile and can drift through the entire structure. Electrons which are capable of moving freely through an empty orbital of the metallic crystal structure are called delocalized electrons, and we can see an example of that in the picture right here. The electrons that might have originally been part of this metallic ion right here can freely pass through the entire structure. So this is a different type of sharing compared to covalent bonds, where electrons are shared between just two specific atoms. The properties that we can expect for metallic bonding include each of the following. Metals conduct heat and electricity very well because they're free-flowing electrons. As electrons enter one piece of the metal, an equal number of electrons can flow from the other end. When light is shown on the surface of a metal, its electrons absorb energy and become excited. The electrons immediately fall back down to a lower energy level and emit light. This process is responsible for the high luster of metals. When a force is applied to a metal, the free-flowing electrons can slip in between the stationary cations and prevent them from coming into contact. As a result, metals are very malleable and ductile. They can be hammered into shapes, rolled into thin sheets, or pulled into thin wires. This, of course, is opposing to what you would have expected within an ionic structure. When an ionic compound is hit with enough force, the ions shift, positives go next to positives, negatives go next to negatives, and it shatters. But with the electrons being mobile here, it is much more adaptable. Due to the nature of metallic bonding, it is relatively easy to introduce other elements into the crystal structure. This forms an alloy, which is a mixture of elements that has metallic properties. Alloys are not compounds since they can be separated by physical means, such as melting. The unique blend in properties gives alloys a wide range of applications. Common alloys you may be familiar with include steel, brass, and cast iron. There are two classifications of alloys. In a substitutional alloy, some of the atoms in the original metallic structure are replaced by other metals that are similar in atomic size. Bronze is a substitutional alloy consisting of copper and tin. So in order for you to have a substitutional alloy, the atoms are going to be approximately the same size. There can be some variation there. In an interstitial alloy, the small gaps in the metal structure are filled in by smaller elements. Steel is a substitutional alloy, consisting primarily of iron and carbon. So in this picture, you can see how carbon, which is much smaller, fits into the little gaps in between the iron atoms. And this leads to unique properties such as the steel being much stronger. The data table below shows common commercial alloys along with their composition of potential uses. This is not the type of information I would ask you specifically to remember, but if you did need to see some examples of some alloys and what they could potentially be used for, you could look back to this within the presentation. For our first checkpoint question, we are asked for a term that describes electrons within metallic bonding. Our term here is delocalized. This term means that the electrons do not have a specific location and they can exist within the entire structure. For number 2, if ionic bonding and metallic bonding result in similar structures, why can metals conduct electricity in a solid state, whereas ionic compounds cannot? Within metallic bonding, electrons are free to move. Within an ionic structure, the ions are locked into place. So the fact that they are not mobile makes the structure a lot more brittle. It also would not allow for the conducting of electricity or heat. Number 3. What is the difference between a substitutional and an interstitial alloy? For a substitutional alloy, the atoms are similar in size. For an interstitial alloy, you have some atoms which are much smaller, which fit into the gaps from the larger atoms. So that concludes our final part of the notes for the unit. A quick reminder of some of the resources that you should be using as you begin to prepare for the unit test. Make sure that you complete all of the practice assignments on KIA prior to the test. If you do particularly poorly on a practice assignment, it is your responsibility to ask questions so that you can improve. In addition to the KIA assignments, you should also make sure that you complete any of the labs and also the Lewis dot diagram practice. Finally, make sure that you check out the YouTube channel for any of the other content creators which have been added. In this unit, we have videos from Tyler DeWitt, Melissa Maribel, Crash Course, TED Ed, and Professor Dave Explains.